So there's two types of primary muscle fiber types. Both of them, all motor units are going to function in a similar manner, but there is a difference in the contractile and metabolic characteristics of these fibers. The two distinct fibers are slow twitch, or also known as type 1, and the other is fast twitch, or type 2. And generally, for most of the scientific literature, they talk about type 2A and type 2B, in which 2A is considered to be fast oxidative glycolytic, and type 2B is fast glycolytic. Generally, the type 1 fiber is considered to be an aerobic fiber, and the type 2 fibers are considered to be anaerobic fibers. Now, in the last 20 years, there's been a tremendous improvement in muscle staining techniques. And what we've seen is that there are many types of subtypes underneath fiber types. So you have numerous fibers that can be considered to be subtypes of type 1, and numerous fiber subtypes that are under type 2. And the difference between these is that depending upon the type of activity, these fibers become more oxidative or more glycolytic, depending upon the type of activity you are performing. So there's a continuum of these subtypes becoming more aerobic or providing more anaerobic characteristics. The type 1 fibers are also called tzivim adumim in Hebrew, or red fibers, because they reflect a greater aerobic capacity, more blood flow. The type 2 fibers, or glycolytic fibers, in Hebrew, generally they talk about tzivim levanim, white fibers that are more the anaerobic type without oxygen. Slow twitch fibers are generally about 50% of the body, and the type 2 fibers are also 50%. The average individual is born about 50-50 regarding type 1 and type 2 fibers, which is the reason why most of you will never be a very good athlete. You may enjoy sports, you may participate in sports, but in terms of being a professional athlete or an Olympic caliber athlete, most of you do not have the genetic machinery in order to accomplish that. Your world-class elite athletes have generally been born with a certain type of fiber type that makes them special in the type of sport that they can perform. For example, your marathon runners are born with a much higher percentage of slow twitch fibers than fast twitch fibers. Your sprinters, Usain Bolts of the world, were born with a higher percentage of fast twitch fibers. Your professional football players, professional basketball players, American football, actually were born probably with a higher percentage of fast twitch fibers than slow twitch. However, if you take that same athlete, and at the end of his career or her career, they say, I want to now run a marathon, they can train to run a marathon, but they will not have the metabolic machinery in order to win the marathon. You can train, compete, and successfully finish a marathon, regardless of your muscle fiber type composition. But in order to be successful and win a marathon, you're really going to have to have a high percentage of slow twitch fibers in order to be successful. So fibers, interestingly, are not changeable. Your type 1, type 2 fibers are not changeable. However, your subtypes do appear to be altered. So you can, depending upon the type of training program you do, you can become more oxidative or more glycolytic, depending upon the type of training program that you're doing, but you can't change the overall fiber type. This is a micrograph, so a photomicrograph showing the type 1, type 2A, and type 2 muscle fibers. Type 2X was a classification used a number of years ago, and it's changed, but it's generally the type 2 is the fast glycolytic fibers. And the darker the stain, the more oxidative the fibers are. So they become more glycolytic they are. So that's you can take a look at. So the type 1 or red fibers, they're more oxidative. It was right the first time. Then white fibers, type 2A, and then the type 2X fibers in gray. 2 years ago, we were very interested out of my lab in the University of Florida. This is actually my muscle on the right hand side here. We were interested in taking a look at a new technique. We did a lot of muscle biopsy work, looking at protein signaling and how different types of training programs can impact that. And we wanted to be able to do multiple biopsies in a single day that surrounds a workout. So we created this technique, and we actually published a microbiopsy method that allows the biopsy to be taken. This subject, right after the biopsy was taken, would then do heavy squat work, and then we take additional biopsies right after the squat and several hours after the squat as well. And we were able to create this technique that you determine what percentage fiber type the person had. So some really interesting data that we were able to produce. We published a number of studies using this methods in looking at what was happening within the body, within protein signaling within the muscle.
Does every person has a different amount of slow twitch fibers and fast twitch fibers?
We have a certain percentage, that's correct. Now, one of the things to keep in mind, certain muscles in the body have a higher percentage of slow twitch fibers versus fast twitch fibers. And that's important for you to understand. You're not born with, say, most people born 50-50, but there's certain muscles in the body that will be primarily oxidative fibers. For example, your postural muscles, the rectus spinae complex of your back, the soleus muscle in your calves, the thoracic, they will be primarily slow twitch fibers for a simple reason. Your ability to stand for long periods of time and your ability to maintain that posture, your diaphragm, if that becomes fatigued like the glycolytic fiber, you would choke to death. You wouldn't be able to breathe. So there's certain fibers in the body, certain muscles in the body that will be, regardless of the type of athlete you are, that will be primarily slow twitch fibers. And again, postural muscles, the respiratory muscles, they have to be highly oxidative, highly aerobic, because if you lose fatigue, you're going to have a major issue regarding supporting life. But the other muscles in the body, your quadriceps, hamstrings, certain other, your biceps, those muscles will vary in terms of the fiber type percentage, and that will be very important. Again, this is the microbiopsy. And then once you have the biopsy, there's a number of things that you can do. This is looking at electrophoresis and eventually looking at a Western blot staining, and then we can determine the myosin isoform to identify fiber type. And this is taking a look at fiber classifications of the type 2A, type 2B, or 2X fibers. And then you look at the characteristics of these fibers. This is important for you to understand. So don't bypass this table. You need to understand the system, the difference between these. And the type 1 fiber is also known as slow twitch or slow oxidative. Type 2A is fast twitch or fast oxidative glycolytic. So understand the different classification systems and understand the characteristics of these fibers. The slow twitch fiber has high oxidative capacity. The type 2 fibers have low oxidative capacity. But the opposite is true in terms of glycolytic capacity. High for the type 2, low in the type 1. Contractile speed. As you might imagine, fast twitch fibers have much greater contractile speed than the slow twitch fibers. But the slow twitch fibers are fatigue resistant. That's important. But the fast twitch fibers become fatigued very quickly. In terms of strength, the fast twitch fibers are more powerful fibers. So if you're interested in a sport that involves strength power, having a higher percentage of fast twitch fibers would be more successful. If we take a look further at the structural and functional characteristics, you can take a look at the number of fibers per motor neuron, the difference between these fibers, the motor neuron size, nerve conduction velocity, contractile speed, the type of myosin ATPase, as well as sarcoplasmic reticulum development. Anything that involves greater fiber recruitment, faster fiber recruitment, faster fiber speeds or power, the the fast-twitch fibers will exceed the type 1 fibers. Anything involved with greater endurance, fatigue resistant, נהיה עייפות, זו יותר צבעים אדומים type 1 fibers.
מה ההבדל בין הסוג השני לשלישי? זה נראה כאילו אותו דבר.
The type 2A, type 2B, or type 2X become more glycolytic or more oxidative. There's gradations of the fiber types. So if we take a look at fiber types that we discussed, it's genetics. If you want to become an elite athlete, choose your parents well. Make sure your mom and dad have a high percentage of fast-twitch fibers if you want to be a sprinter. If you want to run marathons, and I don't know why you'd want to run marathons, but if you do, you make sure your parents have a high percentage of type 1 fibers. As you can see, most of you probably have never met me. I'm a relatively large individual with a background of playing American football. So I was blessed to be able to play at a high level. Running distance was never something that I understood well, enjoyed, and I get pretty bored if I have to run more than 50 meters. So I like the short, high-intensity sprints. Anything longer than 50 meters, as you might imagine. Me and the 2-kilometer bar run in the Army didn't go over very well. In fact, they made a lifetime of trying to research why it was a bunch of crap of having to run 2 miles, 2 kilometers. I actually proved it. The Army still doesn't listen, though. The nice paper published in 1997 how the bar rower is a piece of crap. And I know Oded Bar I knew him quite well. He also said why they still keep on using it. So it was humorous regarding that. But that's a conversation for another day. But if you're interested in being an elite athlete, fiber type is quite important. And you'll realize that you'll hit a wall at one point if you have limits. Now, the average individual has an equal proportion, as we talked about, fast-twitch or slow-twitch fibers, with the endurance athletes primarily slow-twitch and the explosive athletes primarily fast-twitch. Training can create improvements, but not change the percentage slow-twitch versus fast-twitch. It can change subtypes. So the fiber types, you can move them to become more glycolytic, more oxidative, depending upon the type of training program, but you will never be able to change that fiber type.
אתה יכול בבקשה לחזור על ההבדלים בין הסוגים של השרירים בעברית?
Right here. Okay. The type 1, אנחנו דיברנו זה צבעים אדומים, צבעים לבנים, type 2. אתם חייבים להבין את זה וללמוד את זה. יש כל מיני שיטות איך יכול לקרוא את הצבעים בעברית, בדרך כלל צבעים אדומים, צבעים לבנים. בצבעים אדומים, בדרך כלל זה כל דבר שייך לצבולת הוא מצוין. יש לו יכולת גבוהה ב-oxidative capacity, או יכולת צבולת, אבל הוא נמוך באנאירובי. המהירות של קיבוץ הרבה יותר נמוך בצבעים האדומים, אבל יש יתרון שיש יכול למנוע את העייפות. וגם הכוח של יחידת מוטורית די נמוך בצבעים האדומים. בצבעים לבנים זה הפוך. יכולת צבולת הוא די נמוך, אבל יש לו יכולת גבוהה ביכולת אנאירובי, כוח מתפרץ. המהירות של קיבוץ הרבה יותר מהר בצבעים לבנים מהצבעים האדומים, אבל הוא מטייף די מהר, במיוחד צבעים לבנים טייפ 2B. ויכולת מוטורית, כוח מוטורית הוא הרבה יותר חזק בצבעים לבנים. גם הגודל, צבעים לבנים הרבה יותר גדול מצבעים אדומים, זה הסיבה, אחת הסיבות של אנשי צבעות לב ריאה, מרתוניסטים, טריאתלוניסטים, מבנה גוף שלהם הרבה יותר דק מאנשים בכוח מפרץ, הרבה יותר גדול, בגלל הצבעים שלהם הרבה יותר גדול. המהירות של קיבוץ דיברנו הרבה יותר מהר בצבעים לבנים מצבעים אדומים, גם סוג של אנזים, מיוסין ATPase הרבה יותר מהר בצבעים לבנים. הכל מאוד קונסיסטנטית, יציב, כל הסיבות למה הצבעים הלבנים יותר חשוב לכוח מפרץ, מהירות וגודל של השריר. צבעים לבנים יותר חשוב למניעת עייפות, יותר קטן, יותר איטי. אוקיי?
ובתוך סיבים לבנים יש שני סוגים? אני פשוט לא הצלחתי להבין, כי רשום שם...
לפחות שניים. עכשיו, כשהתחלנו לעשות, דיברנו מדענים על פיזיולוגיה של השריר, היה רק יכולת לדבר על 3 סוגים. אדומים ושני סוגים של לבנים. אז בהתחלה, שיפור בטכניקה בתוך המעבדות, אנחנו יודעים יש לפחות 7 סאב-טייפס. 3 בתוך צבעים אדומים, 4 בערך בתוך צבעים לבנים. זה לא מעניין אותי אם אתם יודעים כמה סאב-טייפס מה הם. אתם חייבים להבין שיכול להיות יש השתגלות בתוך כל, יכול להיות יותר צבעות, יותר גליקוליטיק או אנאירוביק, תלוי על סוג של אימונים שאתם עושים. יש סך הכל 2 סוגים, לבנים אדומים, fast twitch, slow twitch, מתחת זה יש מטריה של סאב-טייפס שיכול לגורם השתגלות תלוי על אימונים.
כן, question?
לא שמעתי?
מישהו אחר רצה לשאול?
כן.
I just wanted to know, so the marathon runners would have more slow twitch fibers?
The successful ones, yes.
Okay.
Yes. So you can be a fast twitch guy or gal and still run a marathon if that's what you want to do. If you set your goal to run a marathon, you can do so. But you probably won't win the marathon unless you're running with other fast people. But if you're going to run like the Tel Aviv marathon and you have a couple of Ethiopian runners in there, with the genetic machinery that they're capable of, it'd be very difficult for you to win that race. But if you decided to run a marathon with everybody in certain that were very homogeneous to your population, then the one who trains hardest would be successful.
Okay, thanks.
Mm-hmm. Now this is taking a look at fiber type percentages of various sports on Facebook. You can check it out. At the highest percentage of slow twitch fibers is seen in cross-country skiing, followed by long-distance running. And obviously the sprinters have the lowest percentage of slow twitch fibers and the highest percentage of fast twitch fibers. And you see a degree of variability.
Can I ask another question? Actually, when you try and improve to run a marathon, so what part will improve? Like, can you generate new fibers, or can it change from a white fiber to a red fiber? Like, what will actually change when you improve?
Okay. It's a really good question, Hadassah. We talked about that you can't change fiber types. You can change subtypes. You'll have to take my class next year to really understand it. But there's a lot of adaptations that occur through training that allows you to be better at what you do. There's limitations based upon the genetics of how much you can improve. So we talk about the percent adaptation that we see and how that's dependent upon your training experience. So we can make improvements. There's a limit. There's a ceiling effect of how much improvements that we can make. But there is a tremendous genetic limitation. It doesn't mean that you can't train hard enough to complete a marathon. But like any marathon runner can also perform a sprint. They're just not very good at it. So, what's interesting, certain athletes are required to do both. Example, soccer players, we call kadoregel. I contrast soccer players in America. We call soccer players, the ones that wear dresses, and real football players hit each other in the head all the time. But that's real football. That's just a joke. But soccer players, they actually very interesting athletes because they have to play a 90-minute game. And there's very little substitutions. and they're required to run during the course of a soccer game. The average soccer player will run about 13 kilometers, 10 to 13 kilometers in a game. So it requires a tremendous amount of aerobic capacity. But also keep in mind that that same soccer player, in the course of the game, then to be successful, they have to be explosive to the ball. They're going to sprint in order to get to the ball. Then be able to kick the ball with enough power to allow the ball to get into it. And after doing a lot of research on soccer players, I was in UCF, I did some also in TCNJ, a very healthy appreciation of the athletic ability of these soccer players because they have a combination of a high aerobic capacity and the ability to be really great is to really have a tremendous amount of strength power capability. If you watch the top soccer players in the world, Nehemiah or others, they have the ability to sprint and length of the field unbelievably, and then kick the ball with tremendous amount of power, and run 13 kilometers in the course of the game. That's a unique skill set that not many athletes have. And so I really do appreciate the athleticism of those athletes, and they're ones that actually push the limit in terms of what percentages. And the average individual has a VO2 max. The numbers may not mean much to you, but about 45, 50 milliliters per kilometer of kilogram. Soccer players have about 60, which is pretty good. A marathon runner is about 75 to 80, the elite marathon runner. So you can put it all in proper perspective, what it is. American football players, probably about 45 milliliters per kg. Now, this table, as we move forward, this table reviews the characteristics that we've already gone over. So you can read this at your leisure, but I want to add a couple things that weren't in the previous table. This is, we talked about oxidative, glycolytic, and oxidative capacity. Here's a few more: capillary density, mitochondrial density, myoglobin content, endurance capability. You see that in the type 1 slow twitch fibers, they're much higher here, more conducive to producing energy aerobically than anaerobically. And so again, it's very logical. מאוד הגיוני לשוני בין צבעים לבנים וצבעים אדומים. אם אתם מבינים מה כל אחד פה אומר, אתה יכול לנבא מה התוצאות תהיה לפי צבעים לבנים וצבעים אדומים. אם צבעים אדומים הוא יותר טוב לאימון אירובי או מאמץ אירובי, כל דבר שייך, כל הסתגלות פיזיולוגית שאתם רואים פה, ספיגות קפילרית, ספיגות מיטוקונדריה, ספיגות מיוגלובין, יותר טוב למאמץ אירובי. כשאנחנו רואים את זה בתוך הציר, זה מאוד יציב, התוצאות. Capillary density, mitochondrial density, myoglobin density, endurance capability will all be higher than a type 1 fiber and a type 2 fibers. Now, we talked about type 2 fibers being fast oxidative versus fast glycolytic. Fast glycolytic are the truly anaerobic fibers. They will be all low. Fast glycolytic will be in between the two, so you'll have an intermediate level. Through training, we can push subtypes one way or the other. So as we recruit muscles, we use something known as the size principle. עקרון הגודל. And it's a recruit, a גיוס מאוד מדרגות של יחידות מוטורית, and it's related to the size of the neuron. Smaller units, smaller motor units such as the צבעים אדומים, slow twitch fibers, are going to be recruited for a low force activity. We need a lower stimulus for stimulation, and then as we need a greater force, we begin to recruit the type 2 fibers, more powerful, high velocity movements. This is really important to understand. Really important.
Can you explain it again, please?
The next slide is going to explain it in more depth. So we look at the twitch characteristics of the fibers. The blue fiber is the slow twitch fiber. This lighter blue is type 2A, and the gold fiber is type 2B. So the amount of force being generated and the time, the most explosive fiber, as you can see here, the type 2B. The least force being generated, but can generate over a longer period of time, is the type 1 fiber, called Sirium domain. You can see the twitch characteristics of the differences in these fibers. And here you can see it again on this slide. Type 1, very little power capability. Type 2, a lot more. And type 2B or type 2X, the greatest. Look where the power comes pretty quickly. So the power capability is much different between these types of fibers. However, when we take a look at rate of fatigue, much different. Really a tremendous amount of resilience to fatigue in the type 1 fiber, the slow twitch fiber. Fast oxidative glycolytic fatigue is much quicker, but its fatigue resistance is much greater than the type 2B fiber. So if you're a sprinter, really has a genetic machinery to be an elite sprinter, if you to run even 800 meters, you're probably not going to do very well. But to run that 100 meters, you have the special capability of doing that. But your fatigue under the long distance is quite rapid. Now, in a track and field is very interesting. Every 4 years, people get interested in the Olympics. You have your 100-meter sprinters, which is your elite athletes, Usain Bolt. You have marathon runners. And then you have a group of athletes that are known as decathletes. I forget what it's called in Hebrew. The Eset Tacharut, the machines are called decathlete 10 events. And to be successful, you have to win as many of those as possible in order to get the gold medal. Now, it's interesting. Those events range from strength power to endurance, marathon. So in order to do that, it's remarkable if you think about that. Well, somebody's going to do strength power and also excel at the marathon. You are a jack of all trades, but a master of none, right? Because if you really have the genetic machinery to be successful in one of those, you'd probably be pretty bad in all the others. Still competing with pretty good because you have to be right in the middle. And that's why they're called some of the best athletes in the world, the decathlete, because they have the ability to do it all. Usain Bolt will never be a decathlete because he's so good at being a sprinter that he couldn't possibly run the endurance events. And the one who runs the Olympic marathon wouldn't do well as a decathlete either because he has all the machinery just to do the endurance sports and not the strength power. And this is based solely on the characteristics of their muscle fibers and metabolic machinery. Now, as we begin to recruit more motor units and try to enhance power, there's a ramp-like recruitment of slow twitch to fast twitch fibers. And so the beginning is during light force is primarily going to be the slow twitch fiber. As we begin to increase force, we begin to recruit some of the slow twitch fibers, fast twitch fibers, at maximal effort, we're recruiting all of the fibers within the muscle. And this is an example of the variation of force production with the frequency of stimulation. Just slightly look at it your own time. This also shows the force variation with changes of sarcomere length. This is more, we're just throwing there for interest. And as you go study more biomechanics, and this is something you probably are going to get more in depth with during your career as physical therapy, you understand that as the muscle angle changes, the force capability will change. To give you an example that you may have seen in your life, if you ever performed a bench press exercise, you're lying on your back, supine position, you push the bar off your chest, and also you hit a wall. Well, I can't push any further. Somebody helps you with a couple fingers underneath the bar, you get past that sticking point, and you're able to complete the lift on your own. That sticking point is indicating where failure of the range of motion of that particular length of the muscle, or sarcomere length, is at its weakest. And once you got past that, you were able to now complete the lift because the angle was more conducive for completing the lift based on your muscle. Now the goal is to get stronger at that sticking point. There's exercises, specific exercise that you can do to help the strength at that point. But that's something that if you lift, you'll understand that the changes in how the angle. Every time you perform an exercise, the entire you learn from anatomy and biomechanics, the lever system is going to dictate how much weight you can lift. That lever system is critical. It's within the muscle, but also in the whole organism as well. For example, you put a bar on your back and lower it. That's a class 2 lever system where your muscle is where the axis, the fulcrum, the resistance, and the force. That allows you to lift a tremendous amount of weight. Versus if I put the weight in my hand and try to curl it, is much less because that's the third class lever system. And your ability to lift weights in a third class lever system, it's not as conducive because you have the resistance, axis, and the force. The way that the fulcrum is attached is in comparison to the force and the weight will indicate how much weight you can use. So in the squat exercise, the deadlift exercise, and a more second degree lever systems, versus the third degree, you can lift a lot more weight. The muscle is the same way. But within the muscle itself, the sarcomere length is going to dictate how much weight you can lift on that particular. This is a picture looking at the force velocity curve, also important. This is on the right hand side is the kibbutz concentric, left hand side kibbutz eccentric. And then the y-axis is, the x-axis is velocity, force on the y-axis. At high velocity, very little force is being produced. As you begin to slow down, greater force is seen. The highest force capability is seen during isometric contraction, but even higher is seen in muscle lengthening during the eccentric contraction. So concentric contraction is muscle shortening. Isometric is a contraction, but there's no movement. And eccentric is actually muscle lengthening. So let's put this in practical terms. When you're performing a maximal bench press exercise, what's the speed of movement?
Fast.
It's very slow, right? Maximal, very slow movement. If it's something the weight is very light, you can move the bar very rapidly off your chest. Any exercise, squat, bench press, push press, any other exercise you want to do. If the resistance is light, you can move it more rapidly. If the resistance is heavy relative to your capability, you're going to move it very slowly. You were tested on your maximal capability. Oh, hello. Okay, I don't know. It's weird. Everybody hears me?
I hear you, but we can't see you.
You see my?
Right.
Yeah,
it's fixed now.
Okay, good. All right. So as you move through a maximal exercise, as you're lifting the weight, it's very slow. You got your max. You don't think you can do any more, but you say, "No, I'm going to give it a try." You actually then are able to take a heavy weight. You lower it under control, and then you try to lift it up again, and you fail. This is what you're seeing or experiencing is what you're looking at on the curve here. You got to your maximal ability, but you wanted to try again. So eccentrically, as you lower the weight, that's an eccentric contraction, muscle lengthening. You actually can lift 20% more eccentrically than you can concentrically. So you can lower the weight under control. You can lower the weight under control and about 20%. If you say you lifted, your maximum lift was 100 kilos, and you decided to lift 200 kilos, that exceeds your maximal capability eccentrically. What would happen is the weight would probably come crashing down to your chest. It would not come down under control. I've seen that happen. It's unfortunate, and a cracked sternum is never a good way to start a day. I've seen some guy, a bit of a knucklehead. He said, "I can do this lift," and he winds up not being able to control it. 200 kilos fell on his chest. He wound up being sent to the hospital with a cracked sternum. Not a good day. But generally, it's why when you lift, you need to have an idea as a coach what the person's capability is. Again, maximal strength is seen, the highest force output is seen isometrically. Concentric strength is right below that. A little bit above that is eccentrically about 20%. Okay? High velocities are seen as low power output. High high force is seen at a very slow velocity.
If I understand you, in eccentric contraction, I making more force. I'm
Yes.
doing more force.
Either more force, but the greatest force is seen eccentrically.
All right.
So we talked about 3 different types of muscle contraction: concentric, isometric, eccentric. And that's more for biomechanics. Just want to let you know what we talked about. Again, 3 types of muscle contraction. And we talked about force production. As you increase force production by increasing more recruitment to motor units, and also the increased frequency of stimulation. So it's both. When we get stronger, it's 2 factors that are increasing strength. One is the neurological stimulation and how we recruit, how efficient is the process, and then the size of the motor units, the size of the muscle fibers. So it's the neurological adaptation, and then it's also the skeletal muscle adaptation. Again, we'll talk about that more in depth next year, the next physiology. So we talked about size principle. Your motor units are going to range from low number of fibers in the small to large cross-sectional area fibers and type 2 fibers. And so we generally recruit from slow to fast. However, we can, during explosive lifting, it will bypass a minimal effect of the type 1 fibers. Here's an example of another way that we can take a look at fiber activation. And this is a muscle at rest using an MRI assessment. And the MRI after exercise, the light pixels indicate tissues that were activated. Just quickly, a bit of a taste of what the exercise physiology course we will talk about. If you want to maximize strength and recruiting the higher threshold motor units, you want to work at a heavy intensity. During a 1 to 5 RM, we'll recruit all of the major type 2 fibers in the body. If you can work at 12 to 20 RM, the reason I put this up there is there's too many people here I find don't know how to train. They like to work with repetitions. If you want to be strong, forget about the 12 to 20 RM. You got to work heavy. You got to pump. You got to throw heavy steel around if you want to get strong. If that's your goal. All this will do. Have a high volume exercise. It's only going to recruit the slow twitch motor units. It will not recruit the fast twitch motor units. This is an important concept to see, to understand. Too many people make mistakes. So let's go high volume, and what they're resulting with is it's not very effective. Okay. The more motor unit, the more resistance you use, the greater of the fibers that you will recruit. Okay, I'm going to now move on to an area of sensory fibers within the muscle, and these are called muscle proprioceptors. There are 2 major proprioceptors that we're going to discuss. One is the muscle spindle, and the other is Golgi tendon organ. Both have important roles within the muscle. The muscle spindles are wrapped within the fibers of the muscle, and they measure the stretch of the muscle. The Golgi tendon is a sensory organ that's located in the tendon or the gib, okay, and it measures the force that's being activated in the tendon. Both the roles of these muscle proprioceptors is to protect the muscle from injury. Okay, so as we talked about, the muscle spindles are responsible for monitoring the stretch and length, and the Golgi tendon organ is sensitive to the tension in the muscle tendon complex. Okay, here's a picture of the muscle spindle, these interfusial fibers that are wrapped around the muscle fibers, and they actually are measuring the stretch, and if the stretch is too great, it will cause a sensory response to the brain, and the brain will actually activate the antagonistic muscle group, the opposite muscle group on the joint, to actually contract to reduce the stretch of the muscle. It's an inherent protective mechanism. Okay, there's a tremendous amount of plasticity within the neuromuscular system. We've talked briefly about that. It's not the primary focus of this lecture, That will be for next year. But there are a lot of initial strength adaptations are related to neural adaptation. Generally for the first 6 weeks of training, most of the adaptation improvements in strength are seen through neurological adaptation. And from that point, it's primarily changes in cross-sectional area of muscle size. Skeletal muscle adaptation, again, it adapts to a wide range of functional abilities. Generally, in order to cause changes in muscle size, you have to lift at least 60 to 70% of your maximum force generating capability. As we talked about, generally we start to see changes in muscle cross-section size after 6 to 8 weeks of training. Although there is some recent evidence to suggest it may happen earlier, especially the increase in satellite cell number at the beginning of the training program. But the increase of existing muscle fibers is known as hypertrophy, and the increase in number of muscle fibers is known as hyperplasia. To understand more about this, you're going to have to speak to me next year. As we talked about, the muscle fibers are quite adaptable, both to lack of activity as well as to activity. There's 3 types of adaptations. If you put the muscle in a cast, you have a maladaptation or atrophy. The muscle fibers become smaller. Right? If the muscle is trained, provided sufficient stimulus, it can grow. Either you can grow existing fibers, which is known as hypertrophy, or there is some evidence that there may be an increased number of fibers, and that is hyperplasia. We'll talk more about that at a later time. The hypertrophy is related to an increase in contractile proteins that we talked about today. So as you increase the size of a fiber, that means you're increasing the number of actin, myosin, myofilaments, and also increasing the number of sarcomeres. And this is generally occurs due to the repeated trauma to the fibers from resistance training. And it's the adaptation from the cellular damage that actually causes the increase in protein synthesis, resulting in the anabolic effects of exercise. And this is a number of videos that you can look at in your own time, looking at muscle structure, neuromuscular junction, sliding filament theory, and muscle physiology, talking about troponin, tropomyosin, and myosin cross-bridge cycles. So look at that at your own time. There's no reason for me to watch it. Do it at your own time. If you have any questions now, this would be a good time to ask it. If not, we'll meet again next week.
Excuse me. Can you tell me what you think about effective repetition?
Effective what?
Repetitions.
In terms of resistance exercise?
Yes.
Yeah. For the competitive strength power athlete, I would generally recommend 4 to 6 RM. RM is repetition maximum. So you choose a weight that you can do at least 4 times, but not more than 6. Certain times I go to 6 to 8, but never more than 8 repetitions.
Mm-hmm.
Build is slightly different. Bodybuilding is looking for fatigue development, cause a different type of physiological thing.
And about hyperplasia, it's happen only in when we born, not?
No, the issue behind hyperplasia is an interesting phenomenon. Well, you're going to talk to some. Let me finish this first. Listen. Can you put yourselves on?
לא על מיוט.
Please put on mute.
ניתאי, אתה לא על מיוט.
מה?
ניתאי, סגור את המיקרופון.
אין, הוא תמיד מפריע לי.
מה, נדיר?
Okay.
סגור את המיקרופון, איתי.
סגרתי.
Let me ask the question. It's a good question. What was the question again? What was the question again, please?
About hyperplasia. What the time is happen?
Yeah, the issue behind hyperplasia is interesting because in fat cells we know that hyperplasia occurs in fat cells. That as you fill up the cell, fat cell, once it reaches its full capacity, it begins to divide. And you have more cells, and this is why the yo-yo diets, people lose weight, but they haven't lost the cells. Unless they go back to their old habits, they become even bigger, and they can still continue to divide. So, about 40 years ago, there was an interest in taking a look at whether muscle cells has the same capability. And a guy named Bill Gagne and Duncan McDougall, the two primary scientists looking at this 30, 40 years ago. One was a scientist in Texas, another that was William Gagne, and then Duncan McDougall at Canada, Master University. And the work by Gagne was done primarily in animals, specifically in cats, and in birds. First study is actually in birds. What happens? Ablation studies. In ablation studies, you go into the body and you remove a muscle, and then you sew it up, and the animal lives. And they went back in after several weeks, and they realized that the number of fibers in that animal actually increased as a compensatory mechanism for removing the fibers previously. So based upon that work initially on birds, they said the issue of hyperplasia is something that's possibility. At about the same time, the Duncan McDougall looked at bodybuilders. In the first study, this I think was published in 1988 or 84, he looked at bodybuilders compared to the average individual, and they did a muscle biopsy on these individuals and counted the number of fibers. And in the bodybuilders, they actually showed that the bodybuilders had a greater number of fibers than the average individual. And they attributed that to the training program, that bodybuilders can actually increase the number of muscle fibers. So that was an interesting first study. Saying, okay, if people that train with weights, they have more fibers than people that don't train with weights. But like any good scientist, you want to check your evidence and redo the study, and he did. But this time, he checked it with looking at elite bodybuilders and non-elite bodybuilders. But these two types of athletes were each doing the same training program. And when he did the muscle biopsies in these two bodybuilders, one elite, the other non-elite, he saw that the elite bodybuilders, even though doing the same training program, still had significantly greater muscle fibers than the non-elite bodybuilders. And he realized that those individuals doing the same exact training program, but had a greater genetic disposition for more muscle fibers. So they were genetically able to be a better bodybuilder because simply they were born with more muscle fibers. Bill Gagne continued to do his research and again showed it in cats. Again showed that when you